All right, thank you everybody for attending and showing up for this injection molding with additive manufacturing, specifically looking at the origin technology. Let me turn on my webcam real quick so I can properly introduce myself to everybody. My name is Tim Crennen. I'm a senior application engineer over at GoEngineer. I've been doing additive manufacturing, 3D scanning, in that world for over 12 years. So I've seen a lot, have a lot of knowledge, can answer any questions you guys might have as we go throughout this webinar. If you have any questions, feel free to throw them into the chat, and then I'll be able to see them. We'll address them at the end when we get to that part. And just as they come up, feel free to throw them in there. So we'll go ahead and jump on into this. And we'll start by just saying, let's injection mold some parts. Let's say you had an idea for some parts you wanted to start making. And, let's say it was just this widget thing, something for a board game or something. It's not going to have super high demand. We're going to say maybe 1,000 parts each, something cool. Injection mold, it's going to be 3 different pieces that are all going to fit together. It's not going to take much. They're small parts. It's going to end up being like 3 cents in plastic or something. But then you look to actually get the mold tooling itself made, and that's where all the money in injection molding ends up being, is that expensive, complex tooling. And if we're making something small and cost-effective, just say, be $10,000 to make some tooling for this. And this design actually would probably be too complex for a cheap piece of tooling because of some of those overhangs in there. But ignoring that, if we only do 1,000 parts and it costs $10,000 to make the tooling for it, well, now we went from 3 cents a part up to 10 cents a part. We actually factor the cost of the tooling into there. And that's not even factoring in labor and shipping and all the other fun stuff. So, one kind of brings up the questions like, why is this so expensive? Why is tooling end up being so costly, especially when I just want a small number of parts out of something? So I'm just going to do a real quick intro to injection molding for the people who aren't super aware of it. And basically, it works something like this. It's kind of a cross-section of the process. So over on the left side, we have the the injection ram and the hopper. So the hopper is going to be holding our plastic beads. All right, so it's going to be solid state plastic chunks. Those are going to be fed down into the injection ram. That's going to be heated with a auger screw on it that actually pushes the material forward and heats it, and is able to force, once it melts, force the molten plastic into the cavity of the mold through the nozzle. So the actual cavity, that's the tooling over on the right side, that big square blue block. So that's what ends up costing us, thousands and thousands of dollars to actually get made, just so we can run some sample shots off it, just as if we're trying to verify our design before we go to an even bigger production, or if we're just trying to do low quantities. And then the final casting part is that orange part on the outside there. Kind of in process, this is what it looks like. So you have your auger that spins and pushes material forward and melts it, and then also uses the ram to inject at high pressures and temperatures your material into your cavity. It fills it up, allows it to sit for an X period of time to cool off for the plastic to re-solidify, opens the mold back in half. It's generally the cheap molds. The cheapest ones you can get away with are 2-part molds. And then once it cools off enough for it not to deform, it opens up the mold, kicks it out, closes it, starts it over again. And when you have metal injection molding, you can actually do this very efficiently and quickly. 1,000 parts for an injection mold is actually on the very low side of what you'd ever want to do with these. These are more for, you need 100,000 parts or hundreds of thousands of parts out of a machine. Plastic, you could crank them out on an injection mold machine very quickly. And these prices for getting the tooling made, this has nothing to do with the price of the actual injection molding machine. So that'll all factor into runtime and materials and people actually owning and operating it, or if you have these machines in-house. So the tooling themselves can actually be very complicated, even for something fairly simple. If we take a look at this mold on the right, those little pink and blue parts down there, those are actually being injection molded in that. And you can see how complicated of a setup it is. So we have these pins sticking out for ejector pins. Once the part is cooled, you have to be able to kick it out. With these ejector pins, they have cooling channels going through. You have gating channels. You have where the nozzle is going to be injecting it. You can have that spray out to multiple points on one mold. And all that can end up being very costly. And then that always to say it has to have a very nice, smooth, high quality, high accuracy surface too, so that way the parts don't get stuck on it. So if you are making cheap molds, you can make it out of aluminum, just CNC machines, subtractive manufacturing. The bigger, longer run molds are made out of steel. And you can run hundreds of thousands on these parts, millions of parts before you start seeing wear and degradation. They can wear down over time. You have to get new ones, but that's all for the very big, high production stuff. And this is all assuming you get it right in the first time, right? You have your CAD file, you have it, send it over to the mold maker, they cut it into the tooling, and then you go shoot your parts for the first time. You spent tens of thousands of dollars on this, and then, oh, there was an issue with the CAD file, didn't come out right, doesn't fit. If you're not able to save the tooling and modify it, you'll have to just start all over and get another one going. That can be very expensive. So that's a couple of different areas where rapid tooling can actually come in. So rapid tooling is things like we're using additive manufacturing to 3D print injection molds. So we're not printing the entire mold. You kind of see this big green part, and then we still have a bunch of metal steel parts here. So you can get things for injection mold inserts. So it has the big core cavity. It's got, the ejector pin locations, and then we can just build 3D print or rapidly tool our part to go into it. Traditionally, we used to do PolyJet rapid tooling, because this is one of the good options we had at the time before we had brought Origin 3D printing technology in-house. For Stratasys, the PolyJet could make very smooth, high-quality parts that were great for, you could print up the core and injection mold it. But the problem with that, there was chemistry limitations on the material itself. So they weren't super high temperature materials. They were very smooth and high quality, high accuracy parts we could get out of it. But we have very limited lifespans we could run on these. So we couldn't do very high temperatures. You couldn't do very many shots. You could still verify your design with these. Print it, set this thing up, get this all going for a couple $100. Do, a handful of shots in it, verify that your design works, and then say, okay, now we can go spend $50,000 to have the tooling made and have confidence that's actually going to work well. But now with the Origin technology, we have better options for this because we can do better material chemistries while also still having very smooth, high-quality parts. So here's kind of an example of the Origin technology here, where it's printing up and down this machine. It actually uses DLP technology. So we have a resin vat. It's a liquid photoreactive resin. That's what's in the bottom of those pictures there. Then it pulls the part up out of it, so it builds it upside down. But what we can do with that is we can get very high surface finish. With the unique technologies for the Origin machine, we can actually print any geometry too. So some of the limitations of machines similar to this, technology similar to this, is that they can't do big solid parts. They have to do thinner, spindlier parts, so that way things aren't popping off the build head or going, breaking while it's printing. So the Origin machine can actually print a giant solid block, which is actually that one right there, that big black square that said Origin on it. They can print a block the size of the build chamber out of completely solid material. And that's good because if we're going to be printing injection mold tooling, those are big solid parts. So we can't be worried about, oh, is this going to be too much mass for it to be able to handle? So it can print any size part as long as it fits on the build chamber. And with this unique difference between this and PolyJet, we're actually able to do a higher variety of materials. So we can do higher temperature, higher strength, higher durability materials than we could get on the PolyJets. So all the different machines have kind of their areas that they're strongest. PolyJet's good for full color models, but now we got Origin machines for high quality and high durability and high functionality models. Here's kind of an example of what I was trying to say for how the technology works. So we have our liquid resin there in the light yellow. We have the build head that's going to be pulling it up out of the resin, and we're actually curing through the bottom. So we have a projector that prints the entire cross section in one go, goes up, goes through a glass plate, hits the resin, and then hits the resin and the build head, cures it solid, and then it's able to peel it off of the membrane while keeping it stuck to the build head. And then it goes up, comes back down for the next layer, pulls up, delaminates, comes back down for the next layer, builds it up that way. So what this allows us to do is make cheaper tooling higher quality, cheaper tooling than we're able to do previously. And we can do even really complex ones too. You kind of see a picture on the right there. That is a very complex mold. And they've been able to do, you can print a full set of inserts in 12 hours with the Origin machine. You can do it for a fraction of the price and a fraction of the time you could have for CNCing molds, which allows for faster iterations. So now we're not having something tooled out. Say we're doing a cheap one out of aluminum. It costs us, $10,000, $5,000 to get a real rough one. We do some shots. Okay, let's try an iteration on that. Now we can do all our iterations over the course of 1 week, because it could take weeks or longer or months for CNC tooling to be milled up. And with the high quality, the accuracy and the smoothness we can get off these machines, they've done tests where they've done shots on 3D printed tooling and aluminum tooling and shown them the final parts that came off of those, and people weren't able to tell the difference between those two. So you can actually get very high quality samples to validate your design. Or in situations where you're not doing a super high volume, you could just do full production on it. Again, it's all going to be geometry dependent, what the geometry is, what the temperature material you're shooting into it, and all that stuff. It's not going to work for every situation, but it can work for a lot of them. An example of a company that integrated this into what they were doing is Echo Footwear. And they were actually able to do, they took advantage of some vertical integration. So, they had over 2,000 employees now. They founded in 1963, but they're a footwear manufacturer. And they like staying on the cutting edge of, their technology, and they kind of do an end-to-end cycle for their whole company, from manufacturing their stuff all the way up to selling it. They try and keep it all in-house for that vertical integration, so that way they can leverage their technology, leverage their skills, and be able to, adapt to any challenges that might come up a lot quicker and easier. So one of the new technologies they were looking to add into this and leverage was the direct injection technology that they kind of came up with. They call it DIP. And what they're able to do with this is inject straight into the mold while the upper of the shoe was on the other side of the mold. And then so it builds the sole of the mold into the upper part of the shoe all in one part. So they don't have to then go through later and sew it and glue it on and everything. It kind of comes pre-attached with this method. So by leveraging this technology, they're able to evaluate their designs faster. They're able to, cut costs and time, especially when it comes to high texture details. If you're ever looking at a pair of shoes, and you might notice there's little details on the soft rubber part on the bottom of the shoe. On the side, it might be a stippled texture or different kind of textures built into that. If you're doing a metal mold, that all has to be machined in, and that adds a lot of build time, a lot of prep time. So if you have to machine all the tiny little notches and divots in it versus 3D printing, you can just 3D print it in. Because when you're 3D printing molds, the printer doesn't care on how complex the geometry is, right? That's something that was in CNC, it was directly correlated to price and time. Now 3D printers, when you're printing something more complex, more details, the printer doesn't care. In fact, it actually ends up making the part cheaper if you're able to, use, say, topology optimization or something, cut down the weight and size of parts. You can print actually faster and cheaper, so it's kind of an inverse to how it used to work. And then they were able to evaluate, aluminum molds versus Origin molds when they were first testing this out to make sure it's going to work well. And you can see there's a picture, and this is a realistic picture of taking a part off of an Origin machine. And the reason this is realistic is because you see it's actually covered in goo still, so it's pulling it up out of all the material it's being made from, and it still has that resin on the surface. So it pulls it out, you're going to take it off that build head, you just kind of pop it off, and then you just go wash it in some isopropyl alcohol, and then maybe give it a quick 5-minute UV cure, and your part is ready to go full strength. Most pictures you see on 3D print stuff, they don't show you talk about the post-process. They'll show someone with a completed part just sitting on the tray already cleaned of support. So it comes off the tray. It's not completely covered in, support material. It's not a crazy amount of cleanup. You actually see there's no support material on this either. There's support attaching the mold to the build head on the very top there, and that's it. There's no big support beams going down. There's not a whole bunch of excess breakaway bar support you have to deal with. It's a very easy thing to clean up and take off the tray and go from when it finishes printing to a useful part in a matter of, a couple minutes, to rinse it and give it a quick 5-10 minute UV cure. So lots of benefits on that for the post-processing side. And those, again, one of the main things they're looking for is to be indistinguishable from aluminum-made molds. So that way you can actually, it's competing with that level of technology. So improved surface quality, speed, accuracy, and can do large cross sections, all on the one machine. And when it comes to evaluating this is all very important things, because you can do complex geometry and open resin systems. So if you have your own specific material or something in mind, the Origin machine is completely open system. So if you have a third-party material that some other company is developing, or you want to develop on your own to meet very specific requirements, you can go do that, and you can dial in your own settings on the machine. You can have your own secret sauce if you want. And if you don't want to get into that, they have, we're currently at over a dozen different materials that we can run on the system that are validated and ready to go. There's another probably dozen that are in the, mostly validated stage. And then from there, there's, hundreds of materials out there already that you could just dial in settings yourself, and you could be up and running with it. And again, with this, because they were comparing it to aluminum metal molds, they were able to get the same results off that. So they can do faster iterations, cheaper iterations, get faster time to market, and also improve their designs. So one of the big things when you go to increasing your number of iterations, you can do faster and cheaper, is you get better design, because you're going from, okay, that's good enough, we're running out of time, we're up against the clock here. You can go from good enough to an actual good product. Get to a point where you're happy and you want to move on, and not moving on just because you have to. And depending on the geometry of the part and the temperatures you're shooting into it, you can get thousands of shots. So specifically for Eco, they were able to get thousands of shots into these 3D printed molds without degradation on the mold. And specifically because what they're shooting in, for shoe rubbers are not super high temperature. They're not, high temperature glass filled nylons that are going to wear down the mold really quickly. So it works really well for that. But if we are dealing with very high temperature molds where we want to do something like the glass filled nylons, that higher melting temp, higher pressures, and more abrasive surfaces, we have other materials to do. One of the materials that's available in the open material license is the Perform HW by Covestro. So this is a ceramic filled material. Can still do very high accuracy. It's very stiff, has very minimal warpage, so it holds its shape very well. It has very high heat performance. So this has an HDT of 290 Celsius. And the HDT is when, the temperature of the thing starts to deform and melt when you heat it up to that. But when we're doing shots in it, we have people who do shots into stuff like this at much higher temperatures, because you're not holding the mold at the higher temperatures. You're doing a shot into it. It's holding it for, 5-10 seconds, and then it opens up, kicks it out, and you let your mold cool back off. So people have gotten away with doing 500-degree shots in some of these molds. And, it will lower your overall lifespan on it for number of shots you can get, but it is definitely possible to do shots at much higher HDTs than the material itself. So there's an example of one of the Perform tools, and that's kind of the one we're showing earlier. This is a 20% glass-filled polycarbonate, shot at 150 degrees Celsius into this mold. Very small geometries, fine details in there. They were able to do 40 parts in there with basically no degradation. Now, thanks to the stiffness, the high heat resistance of it, and is actually do real-world kind of applications with that. And that one from earlier at the beginning of the slideshow, we had, you can see all the little details in there. So this is a polyamide 6-shot 270C. Notice that's already above the HDT that we had for the material itself. but because of the small parts and the bigger tooling itself, it's not going to heat up and deform on us. And they did 47 shots out of this, and the only thing they had was a couple little broken edges on the mold, and they're able to easily validate their design, especially for something this complex. Again, the more complex you get, the more it's going to cost a CNC machine versus simple parts. And then when you're able to verify your design on something like this and get your approvals out the door, that just, helps and speeds up everything. And if you're a business that might be doing quotes for people for getting specific ones, this could even be part of the workflow where you can get the customers print out a mold for their part, get sample shots in there for them to approve, within a couple days, and for cheap versus having to CNC something just to get test shots, just to get approvals that way. It's there's lots of ways this can speed everything up. But with that, I mean, in engineering, we don't make mistakes. We just have unexpected learning opportunities. So the more issues you have with molds, in your CAD files, things that you find, that's kind of where the benefits of 3D printing really start showing up a lot too, is when we can do those faster iterations, because we're not making mistakes, we're having learning opportunities. And the more iterations we can do, the more learning opportunities we can crank into one day and get them out of the way faster without having to have them drag on. So with that, that kind of brings us to the end of that little presentation. If anybody has questions they want to throw into the chat, feel free, and I will take a look at those. And if you have any questions you think of later that you want to reach out by email, tcrennen@goengineer.com. Okay, we have some questions in here. So Ryan is asking which materials aren't compatible with the 3D printed inserts. So that just kind of depends on, there's a lot of things to factor in when we're talking injection molded with 3D printing inserts. So one thing is you can't treat it like a metal insert. So sometimes if we're to give a set of 3D printed inserts to a company to test out, we really have to make sure you understand it's not metal, right? So you can't put it at the same clamping pressures, the same injection forces, the same temperatures and stuff. Doesn't work out well. So we have to treat it a little bit more gingerly. As far as compatibility, one thing to factor in is what your mold's made out of versus what you're shooting. You don't want those to, glue together or melt together in here. But the other thing is, so you're going to start, kind of like work up into your mold. So when you're first doing shots, you deliberately undershot. You do lower clamping forces, and you want to kind of like build up to the perfect shot. You don't want to start by trying to like over flash it or anything. And you also take in a couple other things for designing it is, gate placement and things like that. You don't want your gates to be going at as high of pressure, so you might want to make them a little bit bigger, make them not point at, thin features, and not go just through one gate. If you can spread out to more gates going into your part, that helps reduce the pressures and helps prevent distortion and degradation of your molds as quickly. So we have a question. So about the costs and lead times for machine tooling parts and what an estimate cost would be for a set of the Perform mold inserts. So again, it's going to depend on geometry and also who you go through to print them. So if you owned your own machine, it's dramatically cheaper if we were to make something like this. It depends on the size of the part. Basically, if you own the machine, you're just paying for material usage. This part would probably cost, because it ends up being very solid, it's going to use a lot more material, but it's going to cost you, $200 or something or less in material. If you're just printing, if you're to go through a service bureau or something to have them make that for you because you don't have technology in-house and you want to try and get them that way, just figure on them factoring that up by several times, where you'd be looking at, $1,000 or more to have a set of tooling like that made. And again, geometry dependent, company dependent on who you're going to be working with. That is an option that we do offer at GoEngineer is 3D printing services. If that's something you want to reach out to us with, then we can always get estimates and quotes to you for how much it would cost for having us make the parts for you, or if you want to look to getting a machine and try and see the ROI on that, if anything adds up. So we have some questions about what specific materials were used, and it runs the gambit. You can run any kind of materials you want. We've had success with the Perform HW material we can run, which is a ceramic filled material. We've ran other acrylic plastic-like materials that have a high HDT on the machine that can get up to close to 300 Celsius HDT. Those can work well. They all come out with very high surface finishes. It kind of depends on what you need the mold to do and the geometries it needs and the temperatures you're going to be shooting into it. The lower temperatures, basically, the more shots you can get out of a mold. But it also comes down to the causticness of the material. When you have glass filled and stuff, that's going to wear away and grind at your material quicker too. So for the Perform material, all these were printed with the Origin technology. So this is all that DLP technology that works by projecting from the bottom up into a fairly small vat of resin. So you don't need a huge startup cost on how much resin you're getting. And that pulls it up, and it works just like this one, where you can have any different materials. And one of the cool things with the Origin being open material, with these small vats of materials you can put in it, you don't have to have this huge investment. You can actually change out materials, multiple times a day if you want, and it becomes a much more economical process than, say, stereolithography, which we can also do and can also run a Perform material. But that just generally has a higher startup cost, and with stereolithography, you're not changing materials. You have your one material you dedicate to pretty much, and that's the one you're going to be running. Yep. So as I was saying, yeah, with a standard stereolithography 3D printer, you can also print some of these molds. They do have good resolution, high detail. You can get stuff like this, very similar out that. The only issue is you have to have a stereolithography printer to do that. And with that, they use, instead of having a small vat of resin you pull your parts up out of, you actually have a large vat of resin you build your parts down into. And with that means you have a much higher kind of startup cost to get that, because you have to have now gallons and gallons of resin to fill your vat to be building into. But if you are doing a lot of these, if you're a company that does a lot of injection molding tooling, that could be a great option. And Stratasys, GoEngineer, we also offer stereolithography machines. So we have Origin, which is a DLP style P3 machine, and then we have our Neo line of machines, which are stereolithography that can also do Perform material. Peak material would also work well for running this in, depending on, again, what you're shooting into it. With that, I don't think we have any peak materials, at least validated on the Origin machine. But if there were photopolymer versions of that third companies or party companies are making, you can get them and get it dialed in on your own. And then you have your own specific kind of secret sauce you're working with there if you want. Also, the Neo machines for the stereolithography are also open source for material license use. So you can get a giant vat filled of some other material and get that up and running, and you'll be good to go with that. And you can dial in the scanning scheme just like on the Origin system. So the Origin printers, we're looking at, they're about $100,000, give or take. And then you also factor in a little bit of post-processing equipment. And so for cleaning it and UV curing, that's pretty much all you need and you're up and running. There's not a lot of moving parts. There's not a lot of consumables in the machines other than the resin is really the big factor that you're going to be printing with. And then you're up and running. The build chamber size on the Origin machines, we're looking at, it's about 4.5 inches by 7.5 inches is your X and Y, and then 14 inches deep. So you can hang molds in it vertically, but with the Origin technology and the DLP style machines, they're not currently able to do huge build jobs. So we're not doing like the, a 2-foot by 3-foot mold or something on an Origin machine. Now that is something that could be possible on a stereolithography if that is something you really want to get into, because the stereolithography machines can get that big and be able to do the high quality, high temperature, like perform resin and stuff.